So now this is a portion of the combinatories, the pigeonhole principle. Okay, you can guess from its name why it is pigeonhole ना. पिजियन तो मतलब समझते हो कबूतर जो होता है, तो उसका एक्चुअली जो घर होता है, तो उसको लेकर ये प्रिंसिपल एस्टेब्लिश हुआ है. सो दैट मीन्स सपोज n pigeons holes are there, n number of. Okay, suppose we are taking three numbers of pigeon holes here. So these are three pigeon holes, and where the pigeons can occupy, like the bench of your classrooms. So if you all are actually like the pigeons, and the benches are your actually the room or the place to sit. So that means there are the three allocations where you can place. And so this is number 1, number 2, and number 3. These three are the holes for the pigeons, and there are suppose 4 numbers of pigeons are there. Pigeons are there. Now, is it possible to put only one pigeons at a box or at a hole? Is it possible? You have 3 numbers of hole and you have 4 numbers of pigeons. So is it possible to allocate one by one, only one pigeons to each of this hole? Just say it. Is it possible or not? Either it is possible or it is impossible. 3 होल है और हमारे पास 4 कबूतर, तो एक एक करके हम घर में दे सकते हैं, एक एक करके. That only one pigeons at hole 1, only one pigeons at hole 2, and only one pigeons at hole 3. So there is also one pigeons remaining there. So that means we can say that at least one, you can put the every pigeons at room 1, you can put every pigeons at room 2 or hole 2, but we can state that at least one pigeonhole, actually at least one pigeonhole is occupied by more than one pigeons. Is it correct? Is there any doubt? At least one pigeonhole is occupied by more than one pigeons. You can give one by one, na? Am I audible?
Yes.
Yes, sir.
Okay. So if we increase this number to n number, that means suppose n number of pigeons are there, 1, 2, 3, and up to n number of pigeon holes are there, and total n plus 1 numbers are pigeons are there. So these are the holes, number of hole is n, and number of pigeons are suppose n plus 1. Then also the same thing. So obviously at least one pigeonhole is occupied by more than one pigeons. Otherwise it is not possible. तो एक तो होल होगा, पिजियन होल होगा, जहां पर एक से ज्यादा ही कबूतर. तो दिस इज द पिजियन प्रिंसिपल. बेसिक थिंग्स ये हम सब जानते हैं, सिर्फ ये प्रिंसिपल है ये नहीं जानते थे, अब ये भी जान गए कि ये भी एक प्रिंसिपल है. सो द प्रिंसिपल सेज दैट इन एन पिजियन hole are occupied by n plus 1 or more pigeons, then at least one pigeonhole is occupied by greater than one pigeons by more than more than one pigeons. So at least one pigeonhole is occupied by more than one pigeon. यानी कि एक तो ऐसा रूम होगा, एक तो एक होल होगा जहां पर एक से ज्यादा पिजियंस ही है. एंड द जनरलाइज्ड वर्सन इज नाउ द जनरलाइज्ड वर्सन. तो अब थोड़ा सा इनको इंक्रीज कर देते हैं. सपोज इसी तरह से n नंबर ऑफ रूम्स आर देयर, बट दिस टाइम यू हैव 2n plus 1 नंबर ऑफ पिजियंस. देख, अब तुम्हारे पास 2n plus 1 नंबर ऑफ पिजियंस है. तो पहले हम क्या करेंगे, 2n plus 1 नंबर ऑफ पिजियंस को एक एक करके हर एक रूम में दे देंगे. 1 1 1 1 करके, 1 1 1 1 करके हर एक रूम में आ गया. फिर से 1 1 करके हर एक रूम में चला जाएगा. 1 1. दिस इज द मिनिमम पॉसिबल केस, मिनिमम केसेस. एक में ही तुम 2n plus 1 को पुश कर दे सकते हो. 2n plus 1 सब एक रूम में चला गया. दिस इज नॉट नेसेसरी यू हैव टू फिल ऑल द बॉक्सेस. But if you want to fill all the boxes, then the possibility occur, it is here. 1 1 1 all boxes, then again 1 1 1 all boxes. Then this is the 2n case. N numbers are placed here, n numbers are placed here. So that means each box contains now two numbers of pigeons, each boxes. But again we have another pigeons here. You have to place it again, na? So that means at least one boxes will be there who will take 3 or more. Na? We will take actually 3 or more, that means 2 plus 1 or more number of 2 plus 1 or more number of pigeons. More number of pigeons. Okay. Same case, if it is 3n plus 1, then if it is 3n plus 1, then you have to give 1 1 1 again at the row. Then again you have 1 remaining, so you have to put it in the one place. So that means 3 plus 1 number of elements actually in a pigeonhole. So this is the concept. So from here, the generalized case of the pigeonhole principle occur. The generalized case form, it says that if n pigeonhole are occupied by kn plus 1. Okay. So here we set k is equal to 3. In the previous we set k is equal to 2. So this is the value of k. We can change that. Now we use the k. So if it is kn plus 1, then you will put k number of k number of actually pigeons to each boxes. After that you will actually left with one pigeons and you have to put it in any one of the boxes. That means at least one box will contains k plus 1 or more number of pigeons. So this is the generalized case of the pigeonhole principle. So if n pigeonholes are occupied by kn plus 1 or more pigeons, where this k is a positive integer, okay, it is necessary always, it is a positive integer, क्योंकि एक कबूतर है तो ये आधा आधा नहीं हो सकता है. देखिए 1/4 3/4 it is not possible. So this is a whole piece. So this k is a positive integer and then at least one pigeonhole is occupied by k plus 1 or more pigeons. Okay. Now just tell me, is there any doubt on the theorem? After that we will discuss many of its examples, and all are important for exams. We only discuss the important for exam problem. Just tell me, is there any doubt on the theorem? You may have different views also. Just share it with me. Is there any other? हाँ
So,
बोलो.
so I'm saying sir, according to theorem, ये रूल है क्या कि सारे पिजन्स को सारे होल में फिल होना ही
नहीं
चाहिए,
नहीं नहीं,
कि
ऑब्वियसली नॉट.
एक
आई एम
में भी
ऑलरेडी,
फिल हो सकता
नहीं,
है?
हम ऑलरेडी सेज दैट सारे के सारे पिजियन को एक में हम पुश कर दे सकते हैं, सारे kn+1 को. दैट्स व्हाई वी आर सेइंग
पर सर
दैट
थ्योरम क्या कहता है?
थ्योरम कहता है एटलीस्ट वन पिजियन इज ऑक्युपाइड बाय k+1 और मोर पिजियंस. देखो, नॉट पार्टिकुलरली k+1 एक्चुअली पिजियंस. तुम ये कर सकते हो कि एक ही जगह पर सारे के सारे पिजियन को घुसा दिया, ये हो सकता है. तो उन केस में भी तो ये होल्ड करेगा कि k+1 से ज्यादा ही जा रहा है. समझ गए? तुम k+1 से कम नहीं एक रूम में रख सकते हो एक्चुअली. एक रूम, एटलीस्ट एक रूम ऐसा आएगा जहां पर k+1 से ज्यादा ही जाएगा. तो तुम ये भी कर सकते हो कि एक ही रूम में टोटली हमारा सपोज 3 रूम है, हमारे पास टोटल 7 नंबर ऑफ पिजियंस है, हम टोटल 7 को ही एक रूम में पुश कर दिए, बाकी रूम में कोई भी नहीं है, जीरो. तो इन केस में भी तो हमारा जो थ्योरम है वो सेटिस्फाई होता है. थ्योरम बोल रहा है कि एक रूम 2+1 यानी कि 3 और मोर पिजियंस होल्ड करेगा ना, एटलीस्ट एक. theorem state that at least one pigeon hole occupied by 3 or more number of pigeons. तो यहाँ पर तो होल्ड हो गया. तुम तो एक जगह पर 7 pigeons घुसा दिए, इट ऑल्सो होल्ड्स. तुमको ये लग सकता है कि हम यहाँ पर 4 दे दे, यहाँ पर 3 दे दे, बाकी जगह पर नहीं देंगे, तो यहाँ पर भी तो होल्ड हो जाएगा. तो हम मिनिमम केस
जी
को प्रोड्यूस किए थे. मिनिमम केस इज दो दो करके हर एक रूम में, उसके बाद एक तो एक जगह पर देना ही होगा ना, कोई भी एक जगह पर. और जहां भी दोगे तो वहां पर हो जाएगा. देखो, एटलीस्ट वन होल वो एक्चुअली व्हिच कंटेन्स 3 और मोर नंबर ऑफ पिजन्स, 3 नंबर्स ना, तो ये मिनिमम है. दैट्स
यस
व्हाई वी से दैट 3 और मोर, इट इज नॉट नेसेसरी टू फिल ऑल द बॉक्सेस, नॉट नेसेसरी. एक्चुअली ये तो कबूतर है, तो कबूतर आके सारे के सारे एक घर में जा सकता है, वो तो एक्चुअली उनका मर्जी है कहां पर जाएगा.
यस सर, थैंक यू सर.
But at least one whole will contain more than this number of actual elements. Otherwise कोई एक कबूतर बाहर ही रह जाएगा, घर में नहीं आएगा. Like this. यहाँ पर दो दो करके फिल करने के बाद एक तो बाहर ही रह जाएगा. इनको लाना है तो एक में ऑब्वियसली 3 और 3 से ज्यादा होगा. ओके, और किसी का कोई डाउट? If not, then we take some problems. And this is the first problem you may get in your exam. Okay. Uh, just 1 minute. First, we start with this problem. It will be better to understood. Just read it. Find the minimum number of students in a class. To be sure that 3 of them are born in the same month. यानी कि एक क्लास में मिनिमम कितना स्टूडेंट होना चाहिए, जैसे कि ये तुम श्योरली बोल सको कि एटलीस्ट 3 स्टूडेंट्स बॉर्न इन द सेम मंथ, एक ही मंथ में एक्चुअली बॉर्न हुआ है, तो इसके लिए मिनिमम स्टूडेंट क्लास में कितना रहना चाहिए. सो दिस इज द क्वेश्चन. सो दैट मीन्स, सो व्हाट इज द पिजियन होल्स देयर, बोल सकते हो यहाँ पर पिजियन होल्स क्या है. देखो, दो चीज यहाँ से हमको आइडेंटिफाई करना है. हाँ बोलो. यस.
365.
नहीं, सेम मंथ बोल रहा है ना. देखो,
12.
मंथ मीन्स देयर आर 12 मंथ्स ना.
12 months.
So 12 months. So these are the actually our pigeonholes. So this type of January, February, this type करके हमारे पास March, April करके हमारे पास 12 months है. There are total 12 months. Okay, and December तक. So here the total number of pigeonholes, total number of pigeonholes are, that means here the number of n, here n is equal to what? 12. So 12
True.
number of pigeonholes are there, and we are saying that 3 of them are born in the same month, यानी कि three number of student, 3 or more, at least 3 students born in the same month. That means by the pigeonhole principle, here k plus 1 is equal to what? 3. ये तो हम बोल रहे हैं pigeonhole principle में हम बोल रहे हैं कि if total nk plus 1 number students are there, then at least one box or at least 1 month, maybe any one of the month of that, at least 1 month will contain k plus 1 number of students. That means in at least 1 month, k plus 1 number of students have the birthday or born. So here our k plus 1 value is what? 3. That means k value will be what? 2. So number of pigeonhole is 12 and k is equal to 2. So the minimum number of students, just the back calculation of that, minimum number of students is equal to nk
85.
plus 1.
1.
That means n is equal to 12 into 2 plus 1, यानी कि 25. देखो अब देखो, so if 25 students are there in your classroom, तो मिनिमम केस में तुम 2 करके हर एक मंथ में डिवाइड कर सकते हो, उसके बाद भी एक स्टूडेंट लेफ्ट हो जाएगा और जिसको कोई भी एक मंथ में देना होगा. दैट मीन्स एटलीस्ट 3 of them will born in the same month actually. So the 25 is the minimum number of student. If you take 24, देन ये हो सकता है कि दो दो करके डिवाइड हो गया हर एक में, कोई भी एक्चुअली इसमें 3 नहीं है. बट इफ इट इज 25, देन आफ्टर एक्चुअली ऑर्गेनाइजिंग इन 2 ways, you will get left with 1 student and you have to put it at least in one of the month. So this is the usage of the pigeonhole theorem. So the minimum number of student is 25. So if in the classroom there is 25, we can say that at least 3 students born in the same month. Chalo. So now in your classroom there are suppose 70 number of students, na? কতজন আছে ক্লাসে? How many students are there in your classroom?
76, 77.
Okay, 77 number of students. Okay. So 77 number of students are there in your classroom. So that means that this is the total number of pigeons. Total number of pigeons presented in your class. And if we take the month as the pigeonholes for the birthday, so there are total 12 months. So these are the number of holes, pigeonhole. So pigeonhole is 12. So if we divide the equally into each of these actually boxes, each of the month, the minimal case if we consider, we will take the 77 by 12 box function. I think you all are familiar with the box function, na? Box function is
Yes,
the greatest integer function. It will give you the integer value because we already says that k is the integer, na? K is the positive integer. So you can't choose the k as a fraction. So if we take the 77 by 12, this is actually 6. Na? So after giving 6, 6, 6 each of the 12 months, that means total 70 students is already covered. But now we have 5 students left. So obviously we can say that at least 1 month or 7 or more students born in at least 1 month. Born at least 1 month. बोल सकते हैं? देखो तो. From the pigeonhole principle, can we say that 7 or more students born on at least 1 month? 6 तो होगा ही, यानी बाकी जो 5 स्टूडेंट रहेगा ये तो कोई एक मंथ में होगा इसका बॉन्ड, तो जो भी मंथ में होगा उसमें तो 6 से ज्यादा हो गया, तो 6 से ज्यादा मतलब और बाकी जो 5 स्टूडेंट थे, 5 का भी एक मंथ में हो सकता है, यानी कि वो 6 + 5 11 भी हो सकता है, बट एटलीस्ट 7 और मोर स्टूडेंट बॉन्ड ऑन एटलीस्ट 1 मंथ, यानी कि एक मंथ में एटलीस्ट 7 तो हुआ ही है, ये तो हम बोल ही सकते हैं। सो दिस इज द पिजन होल थ्योरम। सो दैट मीन अगर तुम टोटली बर्थडे लिस्ट को ले लो तुम्हारा क्लास को, तो देखोगे कि 7 और उससे ज्यादा स्टूडेंट का एक मंथ में बर्थडे आएगा, आएगा ही आएगा। एंड दिस इज द नेक्स्ट answer to our next question, and this is the next question. So that among all 80 students in our class, 7 or more are born in the same month. To show that, what you have to take? Here you will take, so this is the way of showing. Here nk plus 1 is equal to what? 80. This is the total number of pigeons presented here, and the total number of month n is equal to what? 12. So this is the total number of pigeons, pigeonhole, and this is the total number of pigeons. After that, this nk plus 1, this value nk plus 1 is equal to 80, and where n value is 12, so 12k plus 1 is equal to 80. That means 12k is equal to 79, and k value will be box of what? 79 by 12, since k is the integer value. Okay, so the integer of k, integer value of k is equal to 6. That means by Pigeonhole's theorem, Pigeonhole principle, we can say that k plus 1 is equal to 6 plus 1 is equal to 7, or more students more are born in the same month. Na? Is it clear to everyone?
Yes, sir.
Okay. The next problem. Another type of problem. Instead of the students, if you pick 5 cards from a standard deck of 52 cards, then so that at least 2 will be of same suite. I think all of you know this, familiar with this type of term, deck of 52 cards. That means a set. This deck means actually a set. In every set of actually cards, there will be 52 cards, and actually excluding the joker. And suite means how many suites are there in a card? How many suites? Hey, how many suites are there in a card? Is there no one who can say that? In a card, there are basically 4 type of color, na? 4 type of color card type. One this type of color, one this type of color card, and another color card of this type, and another of diamond type, na? This diamond, spade, clubs, heart. कोई भी नहीं है जो जानते हैं ये सब कार्ड के बारे में? So these are the 4 suites of the card available. So in this type of cards, there are actually 2 of red, 1 of red color, and this is of red color, and these 2 of the black colors. So 2 black suite and 2 red suite of card. And in every of this suite, there will be 13, 13, 13, and 13 numbers of card. So there are total 4 suites, total 4 number of suites, and total 4 into 13 is equal to 52 cards. Now we have to pick 5 cards from the standard pack of 52 cards. So let the card be the pigeons. तो यही तो टेक करना है. So we have to pick the cards. So let card be the pigeon. तो पहले हम वहां पर एक्चुअली दे रहे थे. Now we will pick from the boxes. These two are same things that give something into the boxes and picking something from the boxes. These two are same thing. So now this time we will actually take the pigeons from the boxes. So let the card be the pigeons and let the pigeons hole be the sweets. Let the pigeon holes be the sweets. So these are the pigeon holes now. These are the pigeon holes, and we will select the cards from these pigeon holes now from this chart. So from the 4 boxes, we will take 5 cards. So from 4 sweets, we have to take how many? 5 cards. So obviously you can see that you have to take at least 2 cards from any of the sweets. ना 5 कार्ड हमको ड्रॉ करना है 4 स्वीट से. तो ऑब्वियसली एक एक भी अगर हर एक स्वीट से ड्रॉ कर लिए फिर तो एक तो कोई भी एक इनमें से स्वीट से ड्रॉ करना ही होगा, बाकी जो एक रहेगा. सो दैट मीन्स हियर you have to take at least 2 cards from any of that sweets, and that's our proof that so that at least 2 will be of same sweets. तो कोई भी एक स्वीट से at least 2 cards आएगा. So what we will write? So here we are selecting 5 is equal to 4 plus 1 cards and cards from the standard deck of 52 cards. And while there are 4 suites in the deck of cards. Okay, so this is the principle, general standard principle of the Pigeonhole theorem from where we start this thing. So n pigeons hole, we have 4 pigeon hole, and we have 4 plus 1 is equal to 5 number of pigeons. Then at least 1 pigeon hole is occupied by more than 1 pigeons. That means at least 2 pigeons are occupied at least 1 pigeon hole, and it's actually our need to prove that question. So here we have 4 plus 1 number of pigeons. We have to select from the 4 number of sweets, and here we can say, so here this 5 is greater than 4, so there are at least 1, at least 2 cards are of same sweets. Okay, we are using at least 2, not particularly. Okay, there maybe you can take all the cards from one sweets. You can take all the cards from only one sweets, but there are at least 2 cards are of the same sweets and by the Pigeonhole's principle. Okay, so this is the proof, and by the Pigeonhole principle we have just proved that. So this is the concept of the Pigeonhole principle and where we can use this type of problem. So there may be card problem, there may be ball picking problem in the Pigeonhole, or there may be in some letter and letter box type problem, that some number of letter and some number of letter boxes, and this is also like the Pigeonhole concept. So this type of problem may occur. Here may be some different student number or different numbers appear here, or maybe some different cards maybe appear here, but these 3 problem oriented questions are important for exam. Now just one thing, the principle of inclusion exclusion, you all know that, we just state the principle. You all know the principle of inclusion exclusion. Of inclusion, and this is C, and exclusion. What is principle of inclusion exclusion? If we start with this universal set U, and if this is A and this is B, you all know that the number of element in A union B is equal to n of A plus n of B minus n of A intersection. This is the principle of inclusion exclusion. If it is a 3 set, n of A union B union C, then it will be n of A plus n of B plus n of C, then minus n of A intersection B plus n of B intersection C plus n of C intersection A. Okay, we are taking one minus outside and we are taking common of all these things, and plus 3 element n of A intersection B intersection C. So this is the Pigeonhole theorem. This is the inclusion exclusion principle. So that means we include something, then we exclude something. And you all already performed some of the questions from the set theory and just related to that inclusion exclusion problem. And the basic principle is just the way. That means अब वो देखो एक एलिमेंट में प्लस आता है, then दो एलिमेंट में माइनस, आफ्टर दैट थ्री एलिमेंट में अगेन प्लस, इफ देयर इज फोर एलिमेंट तो थ्री एलिमेंट वन एलिमेंट में प्लस होता, देन टू एलिमेंट में माइनस, देन थ्री एलिमेंट में प्लस, देन फोर में फिर से माइनस. So this is the way of presenting the inclusion exclusion principle. So the general principle is for any number of finite set, any number of finite set, suppose a1 a2 and up to an, union of the set is given by, of the set is given by, is equal to, that means union of number of element in the union of that a1 union a2 union a3 and up to dot dot union of an, this value is nothing but this is the size of sum of size of all single set. Okay, this is the first element, sum of size of all single set, this set, all single set ka sum, minus then sum of size of sum of all size of all two set intersection, then sum of size of all two set intersection, then plus again sum of size of all three set intersection, then again minus sum of size of all four set intersection, and in this way it will continue and up to plus minus 1 to the power n minus 1, this is the sign, and sum of size of n set intersections, or all the total intersection of the set. That means the a1 intersection a2 intersection a3 and up to an. So this is the principle, and it is also holds for not only the 2 3, it holds for any n number in n finite numbers. So this is the inclusion exclusion principle, and the one questions from here. So this is the question, let U be the set of all positive integer and not exceeding 1000. Then find the number of integers less than number of integers less than 1000 and not divisible by 3, 5 or 7. So this is the question. Then find the number of integers less than 1000 and not divisible by 3, 5 or 7. Okay, समझ गए? What is the problem? So U is the total universal set here. This is just a set problem. So this is the universal set. In the universal set, you have total U number of elements. So what is the U? 1000. 1000 integers are there. Positive integers starting from 1 to 1000. And we need the integer which is not divisible by 3, 5 or 7. If we take the A set as divisible by 3, B set as divisible by 5 and C set as divisible by 7, then the union set actually divisible by any of the 3, 5 or 7, and the outsider set actually is the not divisible by any of these things. Na? So actually our question is union, complement of this union set, or if we define the A as A is equal to subset of integers which is divisible by 3 and less than 1000. All are actually less than 1000. So similarly B is equal to subset of the integer same thing which are actually divisible by 5, and similarly C is the subset of the integer which is divisible by suppose 7. Now tell me how many such integers are there? What is the number of A? बोल सकते हो कोई? What is the number of A? N of A? How many such numbers are present there? Less than 1000 and divisible by 3. Is there anyone who can say that how many numbers are there which is less than 1000 and divisible by 3? So there is a formula for finding that. So the formula is the number. So that means number of integers less than k and divisible by prime p divisible by prime number p is equal to box of k by p. Okay. So this is the formula. Box function of k by p. This box is not a simple third bracket. This is a box. This is box function. Okay. So this is the formula. So n number of element of A, such element is so what? 1000 by 3. Now tell me the value. What is the value of that? What is the value of 1000 by 3 box? Is there anyone who can tell me the value? 1000 by 3.
Sir, 333.33.
333. We only take the integer value. N of B.
Oh yes, sir. Sorry, sir. Yes.
N of B is the box function of 1000 by 5. Na? What is the value?
200.
200. N of C. 1000 by 7. Tell me the value.
142.
142.
Okay. Then others, N of A intersection B. Divisible by both 3 and 5 means divisible by 15. 1000 by 15. Numbers?
66.
66. N of B intersection C. 1000 by 5, 7, 35.
35. 28.
n of A intersection C. 1000 by 21.
1000 by 21. 21. 47.
47. Or n of A intersection B intersection C. N of A intersection B intersection C. This is 1000 by 3, 105. Okay.
105.
Value 9.
9.
Okay. So these are the values we have already. So n of A, this is 333. N of B, this is 200. N of C, this is 142. N of A intersection B is equal to 66. N of B intersection C is equal to what? N of B intersection is 28, and then 47 is equal to 28. N of C intersection A is equal to 47, and N of A intersection B intersection C is equal to 9. So now the principle of inclusion exclusion, N of A union B union C, this is equal to nothing but the sum of the single elements 333 plus 200 plus 142 minus sum of the two elements minus 66 plus 28 plus 47, then plus 3 element 9. Now calculate the value and tell me the value. Just calculate it. 333, 200, 142 plus 9 minus this value and tell me what is the value.
543.
543. Okay. So that means this is N of A union B union C. And what is our requirement? Our requirement is a number which is not divisible by 3, 5
N
or
of
7.
U minus of any
So that
union
means
union C.
required value is N of A complement intersection B complement intersection what? C complement. Not divisible by 3, not divisible by 5, and also not divisible by 7. So this is nothing but N of U minus N of A union B union C. So N of U is 1000 and N of A union B union C, this is 543. No. So this is 7, this is
4, 5.
5, and this is 4, 5, 7. So this is the number of integers which is not divisible by 3, 5 or 7, and also less than 1000. So 547's number of integers are present in between 1 and 1000, which are not divisible by any of these 3, 5 or 7. So this type of problems, actually we can say that this is a combinatorics actually problem. This is actually problem of the set, but this is actually in the syllabus of the combinatorics, so we just differently discuss that again.